In this video, I discuss complex variables. What we will do is briefly review complex numbers and functions of a complex variable. The points which I wish to discuss are the following. We shall look at the definition of the ball with center Z0 and radius r. We will look at the derivative of a complex function of a complex variable. We shall look at the definition of a function to be analytic at a point Z0 of the complex plane. What does it mean for a function to be analytic in a region? So this is being analytic at a point, and in this definition, analyticity in a region. We shall have a look at the Cauchy-Riemann equations and its consequences. We will look at the definition of a harmonic function. We will look at the definition of the harmonic conjugates. We will have a look at a certain procedure called as the Milne-Thomson method. And we shall look at the relation between the Cauchy-Riemann equations and analytic functions. This is related to what I just said previously. Regarding Cauchy-Riemann equations and its consequences. So before I start taking up these points, let me recall a few of the things that you must have studied in your earlier classes. So what do we mean by a complex number? So a number of the form z equal to x plus iy, where x and y are real numbers. X is a real number, y is a real number. So such numbers will be called as complex numbers, and we conveniently we can picturize such numbers with the help of what is called as the Argand diagram. So if you think of the xy plane, that can be converted into an Argand diagram. So if you look at the Cartesian plane with x and y as the coordinates, the x coordinate and the y coordinate, this can be thought of as the complex number x plus iy. All right, and therefore you can think of a complex number also as a vector at times. Okay, so let's call this as z. All right, so this will be our complex plane. A complex number will be thought of as a vector or as a point. Okay, what we want to actually do is discuss functions of a complex variable, complex functions of a complex variable. So a function f needs to have a domain and a range. The values of the function are going to be complex numbers. The domain is also going to be a subset of the complex plane. R will be a subset of the complex plane. Now when you talk about subsets, you can have all kinds of subsets, but then we are not going to deal with very weird subsets. Generally we are going to look at very simple subsets. So R, for example, could be the entire complex plane, or what is the counterpart of intervals in the context of real numbers. So we can have rectangles. So R could, for example, be this rectangle. Okay, this could be our R. R could be a circular region. maybe a circle with radius r, circular region with radius r, and so on. These will be some of the commonly occurring domains, which will not be complicated. Okay. All right, so we are going to look at such functions, and in particular we are going to look at functions which are analytic functions. In fact, we are going to discuss mostly analytic functions and functions which are very close to being analytic. All right, so functions which have few singularities. Okay. In order to discuss or write down the definition of a function to be analytic, one should know the definition of the differentiability of such a function. And in order to discuss differentiability, the differentiability is actually going to be a limit process. So one needs to discuss limits, and differentiability and continuity have some relation. So one needs to discuss continuity and so on. All right. Now the definition, or rather the concept of limit, will not be discussed in its complete rigor. If one wants to have a very rigorous look at the definition of the limit, one has to look at the epsilon delta definition given by Cauchy. So we are not going to look at the epsilon delta definition given by Cauchy. We will rather try to develop an intuitive idea about the limit. All right. So in the one variable context, when you say that L is the limit as x tends to a of a certain f of x, what did we actually mean? So if I draw the graph of a function, let me take it to be a continuous function. So the situation is being kept rather simple. Okay, so x can tend to a in its domain, either from the left or from the right. All right. And therefore, if you look at the graph of this function, since it's continuous, you will notice that as x tends to a from the left, the values of the function tend to a certain value. All right. In this case, the value that the function tends to from the left or the right is the same. Okay, and then we call that to be the limit. Now, if a was not a point of continuity, all right, so for example, if there was a break in the graph, okay, so the value that the function tends to from the left may be different. Okay, let's call it L1, and the value that it tends to from the right may be different. All right, let's call it as L2. So in this case, we say that the function does not have a limit, or the limit does not exist. It's a local concept, so everything is happening at A. What happens in the context of the complex functions? Okay. So in the case of the complex function, let us say that this is the domain, and A is a point in the domain. All right. Now, whenever we discuss these local concepts, we need some working space. So we need we need space to work around A, and therefore we make some assumptions about the domain R. And the assumptions are the ones which allow us to work around that point, and therefore R is supposed to contain. So if you take any point within R, there should be a ball completely contained inside the domain. So for example, if I pick this point A, there should be a ball sitting completely inside it. Okay. and it will have a certain radius. I have used the notation BR0 in the notes to come ahead. R is the radius of the ball and Z0 is the center. So what I'm calling at Z0 is actually my A. So this A is Z0. Okay. So such a subset of the complex plane will be called as a region. In fact, it is an open set. People who know about open sets and so on. So this is an example of an open set. Okay. Now this is the domain. This is the Z plane, and its value, the values of the function will be, so W equal to f of Z. W will be another complex number. So we have another complex plane called as the W plane, and the values take place over there. One point which I would like to make over here is that in the case of a function of a real variable, real function of a real variable, we could draw graphs and picturize the function, and many things or many properties, or rather several of the properties, can be read from the graph of the function. Now that kind of a situation is not available to us when you're dealing with complex functions of a complex variable. That is not difficult to understand. The reason being that when you're looking at the domain, you're exhausting two dimensions, one along the x-axis, the other one along the y-axis. When you're looking at W, so you can write W as U plus IV. Okay, so again you're exhausting two dimensions. So if you want to make a graph, we should be familiar with drawing pictures in the four-dimensional space. And this is something which we can't do. All right, so we don't draw graphs of a complex function of a complex variable. You can do something. You can, you certainly cannot draw the graph of the entire function, but then, if you want to have some idea, you can draw sections of the graph. So let me just explain what do I mean by sections of the graph. So for example, if you're looking at f of z equal to z square, all right, what you could do is, so I cannot plot this entire function, so what I do is I can think of looking at the graphs of some of the sections. So for example, what I do is I can fix x equal to 2, and then so x equal to 2 is a line in the domain. So in the z plane we are looking at x equal to 2. So how does the line look after the function has acted on this subset of the domain? Okay, so let's see that. So since f of z is equals z square, which is same as x plus iy square, which is same as x square minus y square plus I times 2xy, let us call this as u plus iv. So this is u plus iv. All right, so what we have is u plus iv is equal to this. So when you put x equal to 2, let's put x equal to 2 in this thing. So u plus iv becomes 2 to the 4 minus y square plus 2 to the 4 I times 4y. Okay, this means that u should be equal to 4 minus y square and v should be equal to 4 times y. All right, let us try to get rid of y. Let's eliminate y from these two equations. Okay, so this means u is equal to 4 minus, so what is y? V upon 4 square, which is equal to 4 minus v square by 16. Okay, so when you look at this, what kind of a geometric object do you get? So if you look at the uv plane, This is the u-axis, this is the v-axis. All right. Clearly, this is a parabola which is opening downwards. So if you put v as 4, 4 4 is 16. Okay. So if you put v as 8 8 is 64. So when v is 8, u is equal to 4 minus 8 8 is 64 by 16. So this is 0. So u is 0. Right. So you have a parabola which is opening downwards, and this particular point is 0, 8. All right. So this particular line takes the shape of a parabola in the image plane, and so on. So you can think of other lines, maybe the ones parallel to the x-axis, or you can take a circle and other things and see what is happening to it. Okay. So in short, you cannot make a graph of complex function of a complex variable. You can get some insight by looking at some sections. Okay. Okay, so let us quickly discuss the limit. So the notations and all are as you have studied previously in the case of a function of a real variable. It's exactly a similar kind of notation is used. So when you write limit z tending to a, f of z is L. So what you mean is that as z approaches a, and now in the complex plane, what is happening is that you have got infinitely many ways of approaching this point a. So you could be approaching a along this curve, or along this curve C2, or along this curve C3, or through any other path. In the case of the real variable, you had only two directions of approach, either from the left or the right. But from the geometry of the complex plane, now it is clear that there are infinitely many ways of approaching a. And if you are saying that a function f has a limit L as z approaches a, the value of the limit must be the same. The value that fz approaches must be the same through all the infinitely many paths, and therefore it makes a much stringent requirement. So limit in the context of a function of a complex variable is a much more stringent requirement on the function f. So L is a point in the w plane, okay, and what I've shown here is, so along C1, if z approaches a along this curve, its image might come along this dotted curve, and suppose it is approaching a certain number L. Look at C2, the image of the function, okay, along, so C2 dash is the image of C2, okay, and the diagram which I've drawn here is that through all these paths, the function is approaching the same value L. Along C3, it is the C3 dash, so it is approaching like this, C3 dash. So if through all the possible paths, all right, the value of the limit L is same, we say that the limit exists. Okay. About continuity, so as in the case of real variables, okay, if the limit is equal to the value of the function at a, you say that the function is continuous. So if limit z tending to a, f of z is equal to a, f of a, you say that the function is continuous. Differentiability also has a similar definition, and the notation is also similar. F dash a means the derivative of f at a, and it stands for limit h tending to 0 of f of a plus h minus f of a divided by h. A is a complex number, h is also a complex number, all right. So if this limit exists, and again it is happening through all the infinitely many paths and infinitely many ways in which h can approach the complex number 0. So if the limit exists, we say that the function is differentiable and f dash a is the value of the derivative at that particular point. Okay, so in the next video I will discuss analytic functions and the remaining concepts.